Bismillahirrahmanirrahim. Today we start chapter number 7, which is related to rotating machinery protection. In our last two chapters that we have discussed in our last 9 lectures, we have covered the protection of transmission line. Here onward we discuss protection of rotating machinery. Rotating machinery includes motors and generators. Mainly synchronous generators are used for generation and induction motors are used for traction application in industries. So that's why our main focus will be on these two machines, synchronous generator and induction motor, where we will also discuss protection of synchronous motors as well. Contents of our today's lecture are: at the start there will be introduction to the rotating machinery. Then we discuss what are the abnormal operating conditions related to the machines which require protection, and out of those abnormal conditions we discuss stator fault today. So there are two types of stator fault: stator phase faults and stator ground faults. Here we discuss these two faults in detail, and then we discuss application of differential protection for the protection of stator of synchronous generator. Then we also discuss the difference between overcurrent differential and percentage differential. Overcurrent differential or simple differential is known as unbiased differential relay, and percentage differential is known as biased differential relay. So expected outcomes: at the end of the lecture, student will learn about the abnormal operating conditions of rotating machines that require protection. Student will learn about the stator faults in machine, what is mean by the stator faults, and student will be able to learn about the application of overcurrent differential and percentage differential for the protection of stators of machines. So in this chapter, all the possible faults and abnormalities in operation of rotating machinery would be discussed. Along with these, the application and design of different relaying scheme will also be part of this chapter. Now it is important to note there are more possible failures or abnormal operating condition for rotating machinery than any other system element. Up to this point, we have discussed protection of transmission line in detail. There was only one problem or one abnormality associated with the transmission line, and that was a short circuit fault. There was no other problem with the transmission line that required protection. But here, in case of rotating machinery, the abnormalities that could cause abnormal operation of the rotating machine and require protection are way more than the transmission line or any other component of power system, because rotating parts have been involved, so possibilities of failures, the type of failures will increase accordingly. Whenever a fault occurs in motors or generator, the consequences or impact on the power system will be huge, but the frequency of occurrence of fault is rare. So now here we make a list of all those abnormal conditions that may require protection in rotating machines. So here these failures that we are going to list over here are common in generators and motors. So that includes stator electrical faults. Electrical faults mean a short circuit fault in the stator. Rotor electrical faults mean short circuit in rotor. Overload condition, that is also common in generator and motor. Abnormal voltages, this problem is also common for motor and generator. And here These problems are only associated with the generators. For example, abnormal frequencies, it has nothing to do with the motors. Such problems are only associated with the generators. Unbalanced loading, overfluxing, inadvertent energization, by mistake energization of generator, failure of prime mover, motoring and startup issue, overspeeding. And following problems are only associated with the motors. That includes stalling or lock rotor condition, single phasing in case of a three-phase machine. If one of the phase is broken, machine is now live only on two phases, that is known as single phasing. Loss of excitation, this problem is only associated with the synchronous motors. Loss of synchronism, this problem is also associated only with synchronous motors. So these are the problems that are associated with the rotating machine. Here if we count from A to O, so large number of abnormal conditions that could occur in rotating machine, but the frequency of occurrence of this fault is not as high as faults in other component of power system. For example, majority of faults in power systems are associated with the transmission line. About 50% of total faults in the power system occurs only in transmission lines. So that is the frequency. But here frequency of occurrence of fault in rotating machinery is much lower as compared to other components of power system. Now out of this list, first we discuss stator faults, and here in upcoming lectures we discuss all these problems one by one. So first we discuss the stator faults. So failure of stator windings or connection insulation can result in severe damage to the winding and stator core. In order to understand what is meant by the stator fault, here I have included few diagrams to give you an idea of how the stator of large machine look like. So you can see here, this is the stator of a large motor or large size generator. Because stator is same in motor and generator, even the construction of motor and generator is same. The only difference is motors convert electrical energy into mechanical energy and generator converts mechanical power into electrical power. Otherwise construction wise there is no difference among these two. So here is another view of the winding. So this white color strands are actually stator winding conductors. So we have covered all these conductors with insulation to provide insulation between adjacent turns of a phase, between turns of different phases, and between the conduct winding and the core. So in this way insulation is provided in stator of rotating machine or stator of motors and generators. So stator fault mean breakdown of this insulation. Now due to the breakdown of this insulation there are three possibilities of fault. Okay, first, if insulation of conductor is broken between the turns of same phase, same winding phase, okay, for example phase A, phase B or phase C, that is known as turn to turn fault. Okay, so that is the least severe fault. And if insulation breakdown occurs between the turns of two different phases, so that will result in a line to line fault inside the stator. For example, short circuit between phase A and B or B and C and C and D, this is known as a line to line fault. And if this insulation breakdown occur between winding and the core, which is essentially at ground potential, that is known as line to ground fault in stator. Okay, in this way turn to turn, phase to phase and line to ground fault can occur in stator, and that is due to the damage of this insulation over the conductor of stator winding. And how this insulation get damaged? So due to aging factor, overloading of machine, that insulation breakdown will occur between either the turns of same phase, or between turns of two different phases, or between the winding and the core. That is another view of stator winding. You can see the conductor and the stator of a large size machine. Okay, now we'll discuss the phase fault protection, how phase faults are protected in case of stator. So remember, I have just discussed how phase fault will occur if the insulation will get damaged between the turns of two different phases. That will be a phase fault. So for short circuit in stator winding, it is standard practice to use differential protection for. So this is the criteria to apply differential protection. Generators rated above 1000 kVA. Okay, so that is 1 MVA generator. If generator rating is 1 MVA or higher, it is standard practice to use differential relay. For motors rated above 1500 horsepower, so for such a large motor, we also use differential relay, or it is recommended or standard practice. Or if motor is rated above or equal to 5 kilovolt, so if motor is a high voltage motor, then it is a standard practice to use differential relay. Okay, if the generator size or motor size is less than these specified limits, then instantaneous overcurrent relay and time delay overcurrent relay can be used to detect the short circuit fault. If short circuit fault current is low, then we use time delay overcurrent relay, and if short circuit fault current will be high, instantaneous overcurrent relay would respond to those faults. Okay, but in case of large size generators and motors, so it is standard practice to use differential relay for stator phase faults. So here we want to discuss that differential protection suits best to the rotating equipment. The differential relay suits best for the protection of stator of motor and generator. Why? Due to two reasons. First reason, the equipment and all its associated accessories such as CTs, circuit breakers, etc. are usually in close proximity to each other. So it is much easier to monitor two ends of our machine because it has a limited size. We can monitor current which is entering and leaving the machine easily. Differential protection requires two ends current to compare with each other and make a decision based upon the difference. So that is not the case for transmission line. So that's why we cannot use differential relay for transmission line if its length of the line is more than 10 kilometer. Second, there is only one voltage level involved. Okay, due to this reason, two side CTs will have equal CT ratio as well as same characteristics. Due to this reason, it suits best for rotating machine, but that is not the case for transformers. In case of transformer, two sides have two different voltage level, two different currents. In order to match the current on two sides, we will have to use CT ratio accordingly. Okay, so it means different CTs are required on two different sides of a transformer. So that's why differential protection suits best for rotating machines, because here the size of machine is finite. We can monitor current at two ends. Second, only one voltage level is involved, due to which the CT ratio would be same at entering and leaving point of equipment. So now this is important to note how we apply differential protection to motors and generators. So first, in case of generators, CTs are used almost invariably located in buses and leads immediately adjacent to the generator winding. In order to understand this thing, I have developed this diagram. Here you can see this is the stator of generator. We have shown the three winding phase A, B, C, and in order to provide protection to the stator of generator, three CTs has been provided in the neutral circuit, okay, and three CTs are provided on the terminal immediately after the winding. So it means this differential relay 87 is providing protection to just this generator stator winding. So this is how differential protection is applied to the generator stator. but case is bit different. The standard that we use for motor is bit different from generator. In case of motor differential circuit, three CTs should be located within the switchgear. Switchgear means where we have installed our circuit breaker and bus is available. So three CTs will be there and other three CTs will be in the neutral circuit of motor. To understand this, here is how we apply differential protection to the motor. Now we can see here in this diagram, here these are the three CTs which have been installed in the switch gear. So it is immediately after the circuit breaker, low voltage circuit breaker. And then comes the cable which will bring the power from that bus to the motor, and then other three CTs are installed in the neutral circuit. So what is the difference between use of differential protection for motor and generator? In case of generators, differential protection just cover the winding of the stator. Okay, but in case of motor, it is standard practice to include the cable or the leads which are connecting the stator winding to the bus. That will also be included into the differential protection. That is the standard that we use to apply differential protection for motors. Now I hope you can understand what is the difference between the application of differential protection for motor and generator. I'm repeating it again. For generator, differential will cover only the stator winding of generator. For motor, differential will also cover that leads or cable which is used to connect the motor with the bus. So that will be part of the differential protection. Now some student may ask this question, then how to provide protection to the cable which is used to connect the generator with the bus? Then we have a separate protection for that cable or connecting leads in case of generator. But generator differential will only cover the generator stator winding, nothing else. But motor differential will also cover the cable which is connecting this motor to the bus. So it is a standard practice that motor rated above 15 horsepower, there are 6 terminals coming out of machine. It means the stator winding is neither connected in delta nor in Y, but we have access to the 6 terminals, 6 end of the winding, 2 for each phase. Then we will make the delta and Y connection of motor. So this is how the terminals are accessible in case of motors rated above 15 horsepower. This is standard practice. Why we have the terminal accessible in this way? So that we can include the three CTs in the neutral circuit. Okay, because here this U prime, V prime, W prime, at these three ends we will connect the neutral point. So how? First we thread these three conductors through the core of the CT and then make a neutral, so that we can insert a CT in the neutral circuit. But if this neutral is already made inside the machine, then that is not possible to insert three CTs in the neutral circuit. So here we have the diagram that shows how differential relay is connected for the protection of stator winding. You can see the current of same phase has been compared at two ends with the help of a differential relay. 3 differential relays are required for 3-phase motors. Now with the help of an example, we'll see how differential relay would provide protection to the stator winding. So for example, here we have shown only one phase of a 3-phase machine, and that is a generator stator, because we have modeled this winding with the help of a source of induced EMF. It is given that the rating of this generator is 125 MVA and voltage level is 15.5 kilovolt and its sub-transient reactance is 0.2 per unit. Based upon these ratings, if we assume that it is a 3-phase generator, then the rated current that will flow through both of the primaries of these CTs will be 4656.19 ampere. This is the normal rated current supplied by this generator to the grid. Based upon this maximum supplied rated current, we will calculate the CT ratio. So CT ratio must be selected in such a way that against this rated maximum current in the CT secondary should not be more than 5 ampere. So closest CT ratio to this current will be 5000 to 5. So this is the CT that we have selected. Now here is the polarity marking on two ends of the CTs. Now, in order to connect the two sides of the CT with each other in differential manner, is a thumb rule. Thumb rule is the two side CTs must have their dotted end either towards the machine or away from the machine. For example, in this particular example, we can see here the dotted end are away from the machine, both sides. This is the first thing. Next, then connect the dotted end of the two sides of CT with each other and non-dotted end with each other. So that connection is known as differential connection. If you are asked to draw the differential relay connection for a three-phase machine, this will be the procedure. Put the dotted end either towards the machine or away from the machine, but that should be same on both sides. Right in this diagram, you can see the dotted end where we have put the polarity marking is away from the machine on both sides. Once it has been done, then connect the dotted end with the dotted end, non-dotted end with the non-dotted end. So that will make a differential connection. Now, according to this polarity marking, the direction of current in the secondary here, that will be away from the dotted, because the main current, primary current, is flowing towards the dotted end in the primary, so secondary current will flow away from the dotted end. On the second CT, which is between winding and the transformer, the primary current is flowing away from the dotted end, so secondary current will flow towards the dotted end. And how much will be this current? According to this CT ratio, these CTs will step down the current by 1000 times. So we get a secondary current of 4.66 ampere. So that is downward, and same current will flow in upward direction in this way. So that is the normal condition. Two currents are perfectly equal in phase with each other. So how much current will flow towards this differential branch? This one, as two currents are exactly equal, which is flowing towards this node and moving away from the node. I'm talking about this node. So total current which is flowing towards the differential relay will be 0. So relay would not operate in that situation. Now let's see a three-phase short circuit fault right inside the zone of protection of this differential relay F1. According to this subtransient reactance and given value of voltage, we can calculate this fault current, and that will be 23,280 ampere, 80.95. There will be no counterpart here in the through the second primary. Here there will be no such fault current to the primary of this CT. So that's why we have this current only in one CT primary. So on the secondary side, we will get a current of 23.28 ampere, which will take this path. Why this current would not be able to flow here to the secondary of this CT? Okay, according to transformer action, if current will exist in the secondary, its counterpart must exist in the primary. But in the primary circuit, we do not have any path for the flow of current. That's why this current cannot exist on the secondary side as well. Now we can clearly see here 23.28 ampere is passing through differential relay. So differential relay can make an easy decision that this is a fault. Reason, because during the normal operation, how much current was passing through this differential branch? 0 ampere. And during the fault condition, how much current is passing through this branch? 23.28 ampere. Now we can set pickup to very sensitive value so that this differential relay can detect a minor fault as well. And that sensitive value for such differential relay will be either 0.1 ampere or 0.2 ampere, or maximum it could be up to 0.4 ampere. So this is the normal pickup setting of differential relay in this configuration, and this differential relay is known as overcurrent differential. That would make decision based upon the current through the differential branch. If current through that differential branch will be greater than zero point 0.1, zero point 0.2 or zero point 0.4, that is the different settings. So 0.1 is the most sensitive and 0.4 is more secure setting. So if current will be greater than that, that is indication of a fault. We have set the pickup to such a low value because it is highly sensitive relay and we get zero current during normal operation. So any current above zero will be a fault condition or due to some abnormal condition. Now let's see what happens if fault occurs right outside the zone of protection of this differential relay at point F2. The level of short circuit is not going to change. The fault current will remain same, that is 23,280.95 ampere. But the location has slightly changed. Now this fault current will flow through the primary of both CTs. So they will produce their replica on the secondary side in this manner. Now we can see here at this node, again the current that is flowing towards the node is exactly equal current that is flowing away from the node. The net current which is flowing towards this differential branch is zero. And this is the beauty of differential relay. There is a fault in the system, but if fault is outside the zone of protection, this relay is not going to respond to that fault. Okay, because two currents are exactly equal, that is being measured by the two CT secondaries. And you have seen the operation of differential relay in this manner in lab experiment number 13, where you have implemented differential relay in MATLAB. So this is how differential relay will work. Even for a maximum fault but outside the zone of protection, differential relay is not going to respond to that fault. Now we'll discuss some problems associated with the differential relay. A relay shown in example 1 would be ideal if the CT always reproduce the primary current accurately. If the things happen according to the discussion that we have just done, then that would be an ideal condition. But nothing is ideal in this world. However, the CTs will not always give the same secondary current for same primary current, even if CTs are identical. Okay. Why this is the case? Here are the few reasons. The difference in secondary current even under steady state load condition may occur due to variations in manufacturing tolerance. No matter which technology has been used to develop those CTs, there will always be difference between two similar CTs. The difference in the secondary loading means the load meters or relay that we have connected on the secondary side of CT, that could be different, and we know that the steady state response or performance of CT depends upon its burden, unequal length of leads to the relay, the cable, small diameter cable that we use to bring the CT secondary current up to the relay, their length can be different for both sides of the CTs. One CT may be close to the relay, other CT may be installed at a distance. So that would result in unequal length of leads. So unequal length of lead means the lead impedance that will be on the secondary side of the CT will become different for two side CTs. So response of two CTs will become different from each other. So unequal burden of meters and instruments that we have connected meters on the secondary side of the CT that may have different impedance value. So these are the reason of unequal response of two CTs during the normal condition, and this difference will further increase during the fault condition. And what is the reason why this difference will further increase? Very high fault current magnitude that may cause the error in CT secondary current, the difference in CT transient response, the DC component in the current, that may result in the transient in CT, and CT may move into a saturation region, and due to this reason we may have different transient response of two side CTs. So this error current flow through the relay, so relay must be set above maximum error current. Okay, now this is an issue. We have seen that in ideal condition, there will be zero current through that differential branch during normal operation and during the fault outside the zone of protection. But due to these factors that we have just discussed, there will be a differential current even during the steady state condition, and that difference current will become further higher if a fault occurs outside the zone of protection of differential relay, because in practical cities CT may get saturated, CT may have error, CT may produce different transient response. So due to these reasons there will be a difference current. So it means now if this is a situation, then that pickup that we have previous case we have set to 0.1 ampere, 0.2 ampere or 0.4 ampere, that pickup should be greater than the maximum possible error current. For case of small motors and in case of small fault currents, that is possible. But in case of large size machines, motors and generators, and for large value of fault current, that is not possible, because that difference current is too high that if we make the pickup setting above that value, then the differential relay will not be a sensitive protection. So it means many faults with small amount of fault current will not be able to be detected by this differential relay. So solution of this problem is another type of relay that is known as percentage differential relay. Here I will introduce what is percentage differential relay and how it is different from overcurrent or simple differential relay. So the differential current required to operate this relay, so the operating current which flows in the differential branch, can be either a constant or a variable percentage of current in restraining winding. So now this concept of restraining winding will be introduced very soon. For example, a relay with 10% characteristics would require at least 2 ampere in the operating winding if the restraining coil current is 20 ampere. So that is the percentage differential relay, and let's discuss with the help of this diagram. So here you can see, instead of using a simple differential, we are using a percentage differential relay, which consists of restraining coils along with the operating coil. So the 87 differential relay that we have seen in previous case, that was just this branch, the differential branch. But here in addition to this one, we have two other coils, restraining coils over here. As its name suggests, restrain, block. So these are known as blocking coil. In order to understand the purpose of this restraining coil and how it will work, just recall the working of induction type relay. So coils that are used in induction type relay, when carries a current, it will produce a torque inside the disc of induction type relay, so that this will rotate in the direction to close the contacts. So that is known as tripping torque. And which force will bring the disc back or retard the operation of this disc? That is the spring torque. So that is known as retarding torque. Now in the same relay, if we add two more coils, when these two coils will carry a current, will produce a torque in the disc in the opposite direction as compared to the tripping torque. Means torque produced by these two new coils will be in the same direction as torque produced by the spring. So that is known as restraining coils. So these coils will oppose the torque produced by the operating coil. But we keep the number of turns in restraining coil less as compared to the operating coil. It means large amount of current is required in order to restrain the operation as compared to the operating coil. So it means the current which is flowing through the operating coil will try to close the contacts, and current which is flowing through the restraining coils, it is going to open the contacts. Now how this percentage differential relay will work? So tripping torque, the operating coil current, would not be able to close the contacts unless this operating coil current is greater than some set percentage of retaining coil current. Okay, now the sentence in previous slide, let's go back to there. Over here it means if retaining coil is carrying 20 ampere current and setting of the relay is 10%, then operating coil require at least 2 ampere to cause a tripping of the relay. If current will be 2 ampere or higher, there would be a tripping. If current will be less than 2 ampere against 20 ampere of retaining coil, there will be no tripping at all. So this is a restraining action. Now when fault occurs outside the zone of protection of such relay, then we can understand that difference current will not be very high, but retaining coil current will be very high. So relay is not going to operate in that condition. Higher will be the fault current, higher will be the retaining coil current, and higher value of operating coil is required to trip the relay, and relay will not be able to trip in correctly in that situation. But when fault occurs inside the zone of protection, then the operating coil current will be very high, maybe equal to or even double of the value of retaining coil current. So relay will easily operate. Now let's see here. If this is current I1 prime and I2 prime, two side primary current, their counterpart secondary currents will be I1 and I2, which will flow through these two retaining coils. And here is the difference current, which will be I1 minus I2. So it means when a fault occurs outside the zone of protection of this relay, that is a very heavy short circuit fault current, that will result in very heavy I1 and I2 current, which is flowing through the retaining coil current. But due to error in CTs, the current which is passing through the differential branch, that will be there, but that current will not be sufficient to cause a tripping of the relay, because retaining coil will restrain the operation of differential relay. But if fault occurs inside the zone of protection, here, if this is the condition, if fault occurs here, then we can see the retaining coil current and the operating coil current, that may become equal. Okay, it means the operating current has become 100% of the retaining coil current, so relay will easily trip in that condition. So this type of relay is as sensitive as simple overcurrent differential, but it is much secure as compared to simple overcurrent differential. Now if we want to implement these characteristics with the help of a numeric relay, so here are the equations that to be implemented. First we calculate difference current, which will be I1 minus I2, the two side current. Then retaining coil current, that will be the average value of current carried by these two coils, I1 plus I2 by 2. That is the definition of retaining coil current. And here tripping would happen if the difference current is greater than the set percentage of retaining coil current. So these percentage settings in electromechanical relay could be 10%, 20%, 30% or 40%. These are the different slope settings. This is known as slope setting as well, or percentage setting. Okay, if it is 10%, what does it mean? Relay would not operate unless the difference current is at least 10% of retaining coil current. If we have selected 20% slope, then it means differential relay would not operate unless the difference current is at least 20% of retaining coil current, and same is the case for 30% and 40%. There is another condition that must be met, and that is I difference current should also be greater than I set minimum. So there are two types of settings in percentage differential relay. One will be I set minimum. This setting is similar to the setting of overcurrent differential pickup setting. Plus difference current should be greater than set percentage of retaining coil current. So once these two conditions are met simultaneously, only then the percentage differential relay will operate. Okay, so these two conditions must be satisfied at the same time. Now let's see response of percentage differential relay in case of a close in but outside the zone fault and a fault within the zone of protection. Here if fault occurs, the first condition at this point just outside the zone of protection of differential relay, how much will be the difference current I1 minus I2? ID will be equal to, if we assume that these two CTs are ideal, so that would be 0 ampere. And if we assume that these CTs are producing maximum error which is not more than 10% according to IEEE standard, CT will be selected accordingly. So we can say that is 0.1 of I1, 10% of this fault current. Okay, this is the value of ID in case of external fault. Now what will be the value of retaining coil current? Retaining coil current will be equal to, if we assume that the same fault current is passing through both of these CTs, that would be I1 plus I1, because we have assumed that I1 is equal to I2. There will be a slight difference, but we have ignored that difference, divided by 2, and IR will be equal to I1. Now what is the value of ID with respect to IR here? ID is just 10% of IR. If we set the slope setting to 20%, this relay is not going to operate for this worst condition where CT is producing as much error as 10% of its rating. So this is, we can see here the difference current is 10% of retaining coil current in this condition, no tripping. Now let's see the second case. If fault occurs inside the zone of protection here, and we assume that this generator is not connected to the system, so that's why there is no contribution from this side, no such contribution. So current through the primary of this CT will be 0. Now let's do the calculation again, that is within the zone fault. So difference current will be I1 minus I2, and if we assume I2 is equal to 0, that is equal to I1. Why I2 is equal to 0 this current? Because here no current is flowing through the primary of this CT. Complete fault current is flowing here into the fault. Nothing is flowing through the primary of the second CT. So ID is equal to I1. And what is the value of IR? That will be equal to I1 plus 0 by 2. We can say the retaining coil current will be 0.5 of I1. Now next, how much is the value of difference current with respect to the retaining coil current? This time difference current or operating current is double as compared to retaining coil current, 200% of retaining coil current. So slope setting is just 20%, and actual scenario is operating coil current is 200% of the retaining coil current. So tripping will occur. Okay, relay will trip for this internal fault. So here we can see it is highly sensitive for within zone fault, and it is not going to operate for fault outside the zone of protection. And this is due to here these two retaining coils and their corresponding currents, retaining currents. Now if we draw the characteristics of differential relay, here we can see on the horizontal axis we have the retaining coil current. The other name to mention this retaining coil current is through current, and on the vertical axis we have differential current or operating current. We can see this straight line here. These are the characteristics set percentage. We can see for different values of retaining coil current in ampere, the corresponding operating coil current is increasing because it is a fixed percentage of retaining coil current. and in this particular situation we can see it is 10%. So here for 2 ampere retaining coil current we need 0.2 ampere of operating coil, for 3 ampere 0.3 ampere, for 4 ampere 0.4 ampere. So due to this reason, now let me explain the difference between simple overcurrent differential and percentage differential current. Here this is the I set minimum 0.1 ampere. In case of simple overcurrent relay, we only have this I set minimum current, the only setting. So it means the overcurrent differential has characteristics like this horizontal line. As soon as difference current will become greater than this level, relay is going to operate. Now if I show you the difference current for different value of retaining coil current in practical CT, that trend will be like this. It is keep on increasing and here will become like this, and this sudden rise in current is due to the CT error, higher CT error, and maybe due to slight CT saturation. Okay, it means up to this level 8 ampere retaining coil current, the overcurrent differential was also working well, but here beyond this value the difference current has crossed the pickup setting in normal condition, so relay would trip in that situation. So we cannot use otherwise we will have to set the pickup setting to very high value somewhere here to accommodate the maximum error current that may make our differential relay insensitive to the minor faults, or we cannot use this relay. But on the other hand, if we are using percentage differential, you can see no matter how higher this retaining coil current is, the tripping criteria, this low, always remain above this retaining coil difference current in normal condition. It is never going to cause the mistripping, or you can say the unnecessary tripping of the relay due to external fault. So this region under this curve is known as negative torque region or blocking region, where differential relay is not going to operate. If operating current will be less than this value for this through current, there is no tripping. Here this line is boundary condition, and here we have the tripping region. So for the example that we have just discussed, we have seen that for a retaining coil current, let's say 4 ampere, we have observed that operating coil current was 200%. 200% of 4 will be 8 ampere, somewhere here, much higher. I have extended this value above 1, so it is even greater than 1, 8 times greater than 1. So relay would easily operate for a fault within the zone of protection. Now in the same graph you can see another curve which is extending in this manner, like here. So in the definition of percentage differential relay, we have mentioned that the setting of relay could be a fixed percentage or a variable percentage of retaining coil current. So if the setting is a variable percentage of the retaining coil current, so characteristic of such differential relay will be this one. Here we can see it is variable. Initially if it was fixed, then it will become, the percentage will keep on increasing, because possibility is there due to such a high through current CT may get saturated. So that's why in those applications where CT saturation could be a problem, instead of using a fixed differential percentage differential relay, we can use a variable percentage differential relay. That is the end of the lecture. So a student asked this question, why differential relay don't cover the cable of stator in generator? I said that this is a standard way to provide differential protection in motors and generators. There will be a separate differential relay for the cable used for the generator, and differential relay that is used for the stator of the generator only cover the stator. That is standard practice. There is no other explanation. It could include that, but standard practice is use dedicated differential for the generator stator winding and separate protection for the cable which is connecting generator with the bus. Normally that size of that cable is not too large in case of generators. The reason, because generators and its associated step up transformer are placed too close to each other. Okay, so there is this physical distance between that step up transformer and generator is not very large. So that's why the second protection that we use to cover the transformer as well, that is known as overall differential. We will discuss it at the end of chapter number 8. That will cover the in between region of generator and transformer.